So good afternoon and welcome everyone. My name is Sierra Lamonaco and I am the Alumni Relations Officer with the Faculty of Applied Science and Engineering, as well as the program lead for the Skule Lunch Learn. I want to thank each and every one of you for being here with us today, especially considering it is our last Lunch and Learn presentation of 2022. Now we have alumni tuning in from all over the world, guests joining us from Canada, Hong Kong, Iran, the United States, and possibly even more. So welcome everyone. Now, before we start today's presentation, I wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still home to many Indigenous peoples from across Turtle Island, and we are so grateful to have this opportunity to work on this land. Now, I hope each and every one of you is excited for today's presentation, as our guest speaker is someone who has shown and proven time and time again to be dedicated to performing leading-edge research with a goal of addressing some critical issues that exist in our society and in the environment. The professor who's joining us today, their current research on developing sustainable processing of materials is an excellent example of how U of T's commitment through the Defy Gravity campaign aims to create a sustainable future for generations to come. Now, a quick housekeeping item: at the end of today's presentation, we will have time for a formal Q&A session. Should you have any questions, please feel free to submit them using the Q&A button below at the bottom of your screen. For individuals who submitted their questions during registration, thank you. Thank you for pursuing your curiosities and sharing your insightful questions with us. We've shared them with the professor before today's presentation and will continue to share them throughout and even at the end of the presentation. Now, before I introduce my partner in crime, I want to take a moment to wish all of you and those dear to you a wonderful, safe holiday season. I look forward to seeing you all again in the future, in the new year. Now, without further ado, it brings me great pleasure to introduce the one and only, the MC and chair of the Skule Lunch Learn program, Laurie Gisele. Laurie is not only an electrical 65 graduate, but he's also someone who is extremely dedicated and engaged member of our alumni community. Laurie has been chairing the Skule Lunch Learn program, and he's coming up to about 10 years now this January, and continues to generously dedicate his time to maintaining our Skule Lunch and Learn's long-established traditions. And with that, please join me in welcoming Laurie Gisele, who will now introduce our speaker for today's event. Thank you.
Thank you, Sierra, for your very warm introduction. Yes, it is my pleasure to welcome our guest speaker today, who is Professor Gisele Azimi. Today, she will be discussing how an emerging green separation technology known as supercritical fluid extraction can recycle e-waste at a low cost and with low energy consumption. Dr. Azimi is a professor and Canada Research Chair in Urban Mining Innovations. She is jointly appointed by Chemical Engineering and Applied Chemistry and Material Science and Engineering departments here at the University of Toronto. She is also a registered professional engineer here in Ontario, where she received her doctorate degree in chemical engineering in 2010 from the University of Toronto. Before starting her academic career in 2014, she completed 2 postdoctoral appointments at the Massachusetts Institute of Technology in the departments of Material Science and Engineering and also Mechanical Engineering. She has been recognized many times with awards for excellence in research, teaching, and leadership, such as the Canada Research Chair that I mentioned, the Emerging Leaders of Chemical Engineering by the Canadian Society for Chemical Engineering, the 2020 Canadian Society for Chemical Engineering Innovation Award, the 2020 Minerals, Metals, and Materials Society Young Leaders Award, the McCharles Prize for Early Career Research Distinction, and here at U of T in the Faculty of Applied Science and Engineering, both an Early Career Teaching Award and an Impact Teacher of the Year Award. With that, it is my pleasure to introduce and welcome Professor Gisele Azimi.
Thank you very much, Sierra and Dori, for the kind introduction. Let me share my screen. Good afternoon, everyone. It's my great pleasure to be here today to present some of the activities on supercritical fluid extraction for the recovery of rare earth elements from secondary resources. My research program at the University of Toronto is at the intersection of process engineering, electrochemistry, and materials design. In terms of process engineering, we look at extractive metallurgy of critical metals such as rare earth elements using pyro and hydrometallurgy. We also look at supercritical fluid extraction for metal recovery. In terms of electrochemistry, we are looking at electrorefining for direct decarburization of molten iron and aluminum batteries. In terms of materials design, we look at high temperature materials for specialty applications, as well as extract and impregnated surfaces for solid liquid extraction. Currently, I train 19 trainees in the form of research assistant, postdoctoral fellow, PhD, and master's students, as well as undergraduate students. I have graduated several candidates as postdoctoral fellows, PhD, masters of applied science and engineering, masters of engineering, and undergraduate students. One of the focal points of my research program is technospheric and urban mining of strategic materials. As for the feed, we look at industrial waste and end-of-life products. For example, red mud from aluminum industry, phosphogypsum from fertilizer industry, and slag from steel making. We also look at nickel metal hydride and lithium-ion batteries, neodymium iron boron magnets, and fluorescent lamps. For extraction processes, we look at supercritical fluid extraction, hydrometallurgy, and hybrid hydropyrometallurgy. We extract rare earth elements, gold, platinum group metals, niobium, titanium, lithium, and cobalt. Today, my talk is focused on the extraction of rare earth elements from neodymium iron boron magnet and fluorescent lamps using supercritical fluid extraction. An introduction to rare earth elements. Rare earth elements consist of a group of 17 elements that includes scandium, yttrium, and the 14 lanthanides. They are classified to light rare earths and heavy rare earths. Light rare earths include scandium plus lanthanum to europium, and heavy rare earths include yttrium and gadolinium to lutetium. The most critical rare earth elements are scandium, praseodymium, neodymium, terbium, dysprosium, and lutetium. Rare earth elements are sometimes described as vitamins of chemistry, as small doses can produce powerful salutary effects. For example, a sprinkle of cerium here and a pinch of neodymium there makes TV screens brighter, batteries last longer, and magnets stronger. Rare earth resources and production rate. Up to 1948, India and Brazil were the main producers. In 1950s, South Africa joined the group. 1960s and 80s, North America. After 1990s, China. As of 2021, produced 60% of the global production from its 35% world reserves. Post-2009, Northwestern Australia, significant deposits of dysprosium that are currently under development. Canada, Greenland, USA, South America, Brazil, India, Russia, Malaysia, and Malawi. Based on USGS 2022, in 2021, production rate of rare earth oxides in tons included 168,000 in China, 43,000 in USA, 26,000 in Myanmar, 22,000 in Australia. That brings the world total to 2,800,000. There are significant growth for magnets, and rare earth metal market was 8 million in 2018, and it is projected to increase to 13 million by 2025, which means 9.3% annual growth rate. Magnets are used for motor drives in electric vehicles, magnets in compressors and motors, magnets in hard disk drives, and magnets for motors and fluorescent use in displays. Some important statistics about rare earths. People around the world change their electronic gadgets as soon as new products are out. That resulted in the production of 52 million tons of e-waste by 2021, which is an increase by 17% compared to 2017, which is an alarming increase globally. Hard disk drives are mostly shredded, especially in the United States, up to 35% because of data security concerns. Recycling could yield 1,000 tons per year neodymium. Many countries are still dependent on China. For example, United States is 59% dependent for its domestic needs, and 75% of this comes from China. Demand for dysprosium and terbium could become extremely challenging. Demand for dysprosium will rise by 2,600 compared with 700 increase for neodymium in 25 years from now. Currently, China is the sole supplier for dysprosium and terbium. Electric vehicles production is more than 5 million which is 63% compared with 2017, which means a very fast growth. Worldwide focus on accelerated production of EVs could be very challenging, especially from demand and supply standpoint. China alone has a plan to manufacture 7 million per year EVs by 2025, which means the demand for neodymium, dysprosium, praseodymium, and terbium could explode. Tesla has announced to use neodymium magnets in its Model 3 long-range cars. There is also increased use of scandium in aerospace industry because alloying scandium with aluminum can make aluminum alloys weldable. Therefore, the use of rivets for attaching airplane pieces will be eliminated. Therefore, the weight and fuel consumption of aerospace industry will decrease. Praseodymium is also predicted to grow at a CAGR of 6.4% because of the increased demand in the aerospace industry, considering that magnesium praseodymium alloys are in engine components. The strategies to deal with rare earth availability are multiple folds. For example, we can bring new mines on board in Alaska, California, Wyoming, and Canada. This involves high capital investment, longer turnover time, and environmental pollutions, as well as radioactivity. We can also rely less on REE magnets or develop non-REE substitutes. Some companies are making effort, for example, Toyota and Fraunhofer, but no commercial success has been achieved yet. We can also look at seabed mining. A Japanese team found a large deposit of rare earths, including dysprosium and terbium in seamud. They are 3,500 up to 3,500 to 6,000 meters deep in the Pacific Ocean. The problem can be damaging the marine ecosystem. Arctic ice melting has revealed significant RE deposits in Greenland, and Sweden and Norway are evaluating this option. And finally, we can recycle RE waste and consumer electronics, and efforts have begun and global communities in favor. Japan has taken the lead. Rhodia in France is recycling multiple RE products such as fluorescent lamps, magnets, and batteries. Mitsubishi recycles AC units, Hitachi recycles AC units and hard disk drives, Honda recycles nickel metal hydride battery, and Apple is recycling its products. Conventional recycling techniques rely on pyrometallurgy and hydrometallurgy. Pyrometallurgy requires high energy input and high reaction temperature. It also produces large volumes of greenhouse gas emissions. Also, value metals partition into slag phase, which must be separated using hydrometallurgy. On the other hand, hydrometallurgy requires large volumes of acids and organic solvents, high operating and maintenance costs due to high corrosivity, and generates large volumes of hazardous waste. Therefore, there is a need for an environmentally sustainable, cost-effective, and efficient process for recycling value metals from post-consumer products. That brings us to supercritical fluid extraction. Supercritical fluid extraction, also called SCFE, is an emerging green technology for the recovery of metals, particularly lanthanides and actinides. A material is called supercritical fluid if its temperature and pressure are raised above the critical points, where the boundary between the liquid and gas phase disappear. Supercritical fluids have several advantages. They have high diffusivity and low viscosity, which are gas-like properties, and high solvating property, which is a liquid-like property. SCFE does not generate hazardous wastewater and acid fumes. We use carbon dioxide as the solvent, which is cheap, abundant, safe, and inert, and easy to vent and recycle. If we look at the inside of the reactor, we see that initially we have a boundary layer between the gas and liquid, and when we increase the pressure and temperature at the same time, the boundary will disappear, and we end up having the supercritical fluid. Applications of the supercritical fluid are as follows. This process was developed in late 1970s to extract and produce high-value products, but it was expanded to less specialized applications. Major commercial SCFE users are energy industry and chemical industry, especially food and pharmaceuticals. Examples include direct liquefaction of coal, enhanced oil recovery from petroleum reserves, coffee decaffeination, vegetable oil production, extraction of organics like alcohol from aqueous solutions, and regeneration of catalyst and activated carbon. This is the process flow diagram of our process. The reactor was manufactured by Supercritical Fluid Technology, Inc. in the United States. We place the feed and a small amount of a chelating agent on top. We close the reactor. The liquid CO2 is pumped inside the reactor. Sometimes we add some co-solvents to the reactor. Then the pressure and temperature are raised above the critical point. When we reach the set temperature and pressure, sufficient time is allowed. And after that, the system is depressurized, the sample is collected in a collection vessel, and the CO2 is leaving the sample because of depressurization. There are various solvents that can be used as supercritical fluids. Examples include carbon dioxide, water, methane, ethane, propane, and ethylene. Here in this work, we choose carbon dioxide because of its moderate critical temperature of 31 degrees C and critical pressure of 7 megapascal. Supercritical CO2 is a non-polar solvent. Metal species need to be charge neutral and coordinatively ready to dissolve. Metal ions are positively charged, so they must be bonded with a negative ligand or a combination of negative and neutral ligands. Metal ligand complex is nonpolar and soluble in supercritical carbon dioxide. This is an example. Here we have neodymium 3+ at the center. We bond that with 3-nitrate as neodymium nitrate. And we also ligand that or chelate that with 3-tributyl phosphate or TBP molecules. Each of these has an aliphatic chain, 3 aliphatic chain. So we form a reverse micelle with 9 aliphatic chains. And this is a nonpolar compound that can be dissolved in supercritical CO2. Several studies in the past have looked at the recovery of rare earth elements from mixed oxides or pure oxides. Only a few have looked at the recovery from real products. For example, Shimizu and Masorelli looked at fluorescent lamps, but the extractions they achieved were low. And my group has looked at nickel metal hydride battery, neodymium iron boron magnet, and fluorescent lamps with promising extraction efficiencies. The first project I want to show to you is the recovery of terbium, europium, and yttrium from real fluorescent lamp waste using supercritical fluid extraction. This project was conducted by my PhD student Jikai, my former PhD student Dr. Anabati, and myself. Fluorescent lamps dominate the lighting market because of the 75% lower energy consumption and 10 times longer life. Up to 8% of the total weight of fluorescent lamp phosphors are rare earth elements, mainly terbium, europium, and yttrium. The rare earth content in waste fluorescent lamps is over 10 times higher than the minimum industrial grade for primary ores, which is 1.5 to 2 weight%. The blue and green phosphors are resistant to attack by acid because they comprise insoluble phosphate compounds. In many cases, the residue is discarded after leaching the red phosphor, although it contains considerable amount of valuable terbium that can bring more economic value to the fluorescent lamp recycling process. The objectives of this study were to develop and optimize the SCFE process for recycling terbium, europium, and yttrium from waste fluorescent lamps. Also to utilize pretreatment methods to maximize the extraction efficiency of terbium. Finally, to perform a thorough characterization of fluorescent lamp samples before and after supercritical fluid extraction to elucidate the process mechanism. We obtained the waste lamp phosphors from a local recycling company called Ontario Lamp Recyclers. The as-received phosphor powders contain large particles, mainly glass and aluminum foil, so they were separated by sieving, and less than 75 micron fraction was used in the experiments. We used TBP HNO3 adduct by mixing TBP and HNO3 and separating them in a separation funnel and collecting the organic phase. This complex contained TBP with 0.6 molar H2O and 9.6 molar HNO3. We used design of experiment to design our experimental matrices. Here we had 5 operating parameters: temperature, pressure, duration, solid to chelating agent ratio, and agitation rate. At the end, we form empirical models, we construct empirical models, and we connect the extraction efficiency of the target metals to the operating parameters. That can allow us to optimize the process. We first conducted X-ray diffraction analysis to identify the crystal structure of the sample. We found that it contains red phosphor, green phosphor, and blue phosphor. Red phosphor is yttrium europium oxide. Green phosphor is phosphate of cerium, lanthanum, and cerium, and terbium, and aluminum cerium oxide. And the blue phosphor is barium, magnesium, aluminum oxide. Most studies in the past focused on the recovery of yttrium and europium from the red phosphor because of their high economic value. But green phosphor was discarded because it contains phosphates that are not soluble in acid. We obtained the compositional analysis by digesting the sample in achroragia, which is a strong acid, and measuring the concentrations with ICP-OES, inductively coupled plasma optical emission spectroscopy. We saw that this sample contains 28 weight% yttrium, 1.9 weight% europium, and 1.3 weight% terbium. Based on this chemical composition and XRD determined phases, we obtained this composition for the feed in terms of yttrium oxide, europium oxide, or the rare earth phosphates. We performed supercritical fluid extraction using the DOE matrix. We had 11 tests, and we observed a 34% extraction for yttrium and europium and 16% for terbium. So in this case, we showed the feasibility of recovering rare earth elements from these fluorescent lamp phosphors using SCFE, but the extractions were low, so we needed to improve them to make the process economically and industrially attractive. To enable this, we use mechanical activation by high-intensity oscillation milling. The objective was to increase mass transfer rate, therefore extraction, by introducing structural defects, phase transformation, and amorphization. Phosphor samples were oscillated at 30 Hz for 15 to 120 minutes in a tungsten carbide jar with 2 tungsten carbide grinding balls. After mechanical activation, we performed SCFE, and we saw that the extraction efficiencies are improved by 20 to 30%. We looked at the effect of mechanical activation on particles. Here you can see SEM or secondary electron microscopy images of the particles before mechanical activation and after mechanical activation for 60 minutes. We see obvious increase in surface roughness after mechanical activation. We also observe smaller particles with visible damage to the particle surface. We have higher magnification images. Here the scale bar is 500 nanometer. We also here observe obvious increase in surface roughness after mechanical activation. We looked at these materials under high resolution TEM. And here for before mechanical activation, we see that atoms are organized in a perfect lattice array. They are repeating in repeating arrays over the entire extent of the material, and no nanocrystallites are observed. However, after mechanical activation, we observed a reduced crystallite size and nanocrystallites of 10 nanometer or less, and lots of grain boundaries in the material. A small degree of amorphization is also observed at the edges of the particles and grains with different crystallographic orientations. So in comparison with amorphous content, the polycrystalline material accounted for most of the particle. Mechanical activation reduces crystallite size and creating defects. Dislocations, unidimensional defects, and grain boundaries provide diffusion pathways within the treated material. This enhances the diffusion of adduct and supercritical CO2 to the particle, which improves the extraction efficiency. In summary, management of spent fluorescent lamps in an environmentally sustainable approach can reduce the volume of landfill waste. It can mitigate the environmental and health concerns as fluorescent lamps are toxic and hazardous waste. It enables the recovery of terbium, europium, and yttrium and reduce reliance on environmentally harmful primary extractions. We observed that the presence of aluminum oxide and calcium phosphate hydroxide in the waste fluorescent lamp reduces the extraction efficiency because of the competing reactions between aluminum 3+ and calcium 2+ ions and TBPHNO3 adduct. To enhance the extraction efficiency, we pre-treated the fluorescent lamp feed using mechanical activation. Under the optimum conditions, more than 70% europium and yttrium and 58% terbium extraction efficiency is achieved, which is higher than the reported in literature. The second project is focused on the extraction of rare earth elements from neodymium iron boron magnets. The project is also conducted by Jikai and John Anavati, and also Bill Yao, my former MASC student. The objectives of this study were to characterize crushed and demagnetized N52 neodymium iron boron magnets, to investigate the feasibility of RE extraction from the magnet using supercritical CO2 with TBPHNO3 adduct, also to determine the optimum operating parameters, and finally to propose a mechanism behind the process. Neodymium iron boron magnets are widely used in wind turbines and electric vehicles. They contain 22% weight rare earth elements. There is a forecasted increase in EVs from 2.3 million units in 2016 to 10 million units in 2026. Global wind energy is also expected to increase from 486 gigawatt-hour in 2016 to over 800 kilowatt-hour by 2021. We obtained N52 magnets. We demagnetized them at 350 degrees C in a furnace, and we removed the coating, and we crushed and ground the sample. We digested that in acregia, which is a strong acid, and we measured the composition of the metals using ICP-OES. This is the composition. It mainly contains neodymium, praseodymium, dysprosium, and iron as impurity. We looked at the particles under SCM. This is a SCM image, and we see elemental mapping. The gray areas are the dark gray areas are iron and dysprosium, and light gray areas are neodymium and praseodymium. Again, we use design of experiment containing 7 parameters: temperature, pressure, duration, solid to chelating agent ratio, agitation rate, chelating agent, and methanol addition. To calculate the extraction efficiency, we measured the composition of the sample before and after a CFE, and by subtracting them and dividing them by weight percent of unextracted sample, we obtained extraction efficiency. The stoichiometry of neodymium ligand complex was determined by UV visible spectroscopy, and water and acid content of the adduct was measured by acid-base titration and Karl-Fischer titration, respectively. Here we see graphs of the effect of operating parameters on two metals, iron and neodymium. Neodymium is the representative of neodymium, praseodymium, and dysprosium. Here we build empirical models that connect the extraction efficiency of each metal to the operating parameters. The bar on the right-hand side of this graph show the parameters that have positive impact on the extraction efficiency, and the ones on the left show negative impact. Any bar that has the error bar crossing the zero line has statistically insignificant effect. And these graphs in the inset show the model prediction results versus experimental results. Here we see that, for example, for neodymium, X6 and X4, that are the acid content in the adduct and solid to chelating agent ratio, have the most positive impact on neodymium extraction. But these two parameters have no effect on iron, so we can control them to increase extraction efficiency of rare earths by minimizing co-extraction of iron. On the other hand, X3 and X2, that are time and pressure, have the highest positive effect on iron. So iron extraction is controlled by parameters that increase the magnet solubility in supercritical CO2, whereas rare earth extraction is controlled by the degree of complexation with TBP-HNO3 adduct. Under the optimum operating parameters that are shown in this table, we obtain more than 80% extraction of rare earths with less than 40% co-extraction of iron. Here we propose a mechanism for extraction process. We say that the nitric acid attacks the metals, for example, neodymium, and it forms neodymium nitrate, so NdNO3,3. And this neodymium nitrate bonds with 3-TBP, forming this reverse micelle that has 3 nitrate and 3 TBP, and TBP has 3 aliphatic chains. So we have a reverse micelle with 9 aliphatic chains pointing outward, and this is a nonpolar compound that is soluble in supercritical CO2. Iron can form iron 3 and iron 2. Iron 3 behaves exactly like neodymium 3, so we will have iron 3 with 3 nitrate and 3 TBP molecules. But iron 2 forms iron nitrate 2, and here we hypothesize that the number of TBP molecules are 2, so iron 2 nitrate TBP2 has only 6 aliphatic chains, so iron 2 has a lower solubility in supercritical CO2 because of the reduced number of aliphatic chains. Since iron occurs in 2 valences, the extraction of iron would be lower than the extraction of the rare earths that occur only in 3 that have higher aliphatic chains. Later on, we prove this structure with DFT modeling and XAS characterization. In summary, neodymium iron boron magnet has around 23 weight percent rare earth elements. The rare earth content of the magnet can be extracted using supercritical CO2 with TBP-HNO3 adduct. The optimum operating conditions are 55 degrees C, 21 megapascal, 1 hour, creating solid to chelating agent ratio of 0.1 grams per milliliter, which results in more than 80% dysprosium and neodymium extraction. A mechanism for the supercritical fluid extraction is proposed. The next project is in the continuation of the project 2, and here we investigated the effect of organophosphorus ligands. So using ligands in addition to TBP or besides TBP on supercritical fluid extraction of neodymium from the magnet. This project was also conducted by Jikai and one of my undergraduate student, Kimberly, and this was in collaboration with Professor Shimoyama from Tokyo Tech University, and he sent his PhD student to my group as a visiting research student, Natanai, who has graduated with a PhD degree. Here, the objectives were twofold: to predict the solubility of ligands in supercritical CO2 using COSMO-VAC thermodynamic model, and to determine the stoichiometry of neodymium ligand complex in supercritical CO2. These two goals can enable investigating the combined effect of organophosphorus ligand solubility in supercritical CO2 and neodymium ligand stoichiometry chemistry on the extraction efficiency of neodymium from the magnet. Magnet used in this study was N52 neodymium iron boron magnet, similar to Project 2. And here we use 4 organophosphorus ligands: triethyl phosphate or TEP, tributyl phosphate, which we were using in previous project, TBP, tributyl phosphinoxide, TBPO, and trioctyl phosphinoxide, TOPO. To make the ligand an HNO3 adduct, we mix the ligand, the 4 ligands that I mentioned previously, separately with 78% nitric acid. We vigorously shake it and leave it for 10 minutes to do the phase separation. The 2 phases, organic and aqueous phases, separate, and we collect the upper phase as the organic phase. This is the schematic of the process that I also showed before. This is the reactor. In this process, we only use supercritical CO2, so we pumped liquid CO2 with no co-solvent. And after the process was complete, we collected the sample in collection vessels and CO2 was released. Here we had 6 operating parameters: temperature, pressure, duration, solid to chelating agent ratio, agitation rate, and chelating agent. Again, to calculate the extraction efficiency, we measured the concentration of the sample before and after extraction with ICP-OES. We determined the stoichiometry of the neodymium with the ligand complex using UV vis spectroscopy, and we characterized the ligands for water and acid determination using acid-base titration and Karl-Fischer titration. We use COSMO-VAC thermodynamic model to calculate the activity coefficient that depends on the density of CO2 and system temperature. At low pressure supercritical CO2, we have a high non-interact space, and at high pressure supercritical CO2, we have low non-interact space. Here we use this model and we calculated the solubility of, or predicted the solubility of, these 4 ligands in supercritical CO2. And we see that TEP is more than TBP and TBPO and higher than TOPO. If we look at the molecular structure of these 4, we see that the solubility decreases from TEP to TOPO, and that is due to the increased interaction between the ligands through van der Waals forces, which decreases the interactions with supercritical CO2. We also determined the stoichiometry of the ligand in neodymium ligand complex using UV-Vis. Here we made solutions of neodymium nitrate, and we added predetermined amount of the ligand, for example, TEP or TBP to that, and we measured this absorbance of the complex at 585 nanometer. And this absorbance at this wavelength arises from the hypersensitive FF transition of this atom. You see that the absorption increases by increasing the ligand to neodymium ratio, and after a certain point, it reaches a plateau. The point that these 2 lines cross each other is the number of the ligand. So for TEP, we have 1, TBP, we have 3, TBPO, we have 3, and TOPO, we have 4 in the complex. We use these 4 ligands and we performed extraction efficiency. We perform extraction process using supercritical CO2, and we observed highest extraction with TEP, more than TBP, more than TBPO, and more than TOPO. The mechanism behind these results is twofold. One is the solubility of ligand. The higher the solubility, the higher the extraction efficiency. The second was its complex size. The larger the complex, the lower the extraction efficiency. So high ligand solubility in supercritical CO2 and low coordination number around the cation, which results in no formation of superaggregates, results in higher extraction efficiency. On the contrary, low ligand solubility in supercritical CO2 and high coordination number around the cation, which results in the formation of superaggregates by hydrophobic interaction between aliphatic functionalities, results in low extraction efficiency. Increasing the stoichiometry of the ligand in complex results in higher hydrophobic interactions between aliphatic functionalities. So we have larger micellar assemblies that have lower solubility in supercritical CO2. The solubilities are as follows. Neodymium nitrate 3, TEP1, is higher than neodymium nitrate 3, TBP3, higher than neodymium nitrate 3, TBPO3, higher than neodymium nitrate 3, TOPO4. In summary, organophosphorus ligand solubility in supercritical CO2 was calculated using COSMOVAC model. The order of solubility was found to be TEP more than TBP, equivalent to TBPO, higher than TOPO. The stoichiometry of neodymium ligand complexes was determined using UV-Vis spectroscopy. Complex chemistry was found to be 1:1 for neodymium TEP, 1:3 for neodymium TBP, 1:3 for neodymium TBPO, and 1:4 for neodymium TOPO. Neodymium extraction from neodymium iron boron magnet decreased with increasing coordination number. And the most current study that we performed was a structural study of complexes formed by tributyl phosphate. This work was completed by Jikai. As you can see, he has been working with me for quite some time. He started his first project as a summer student in the second year. Then he did his undergraduate thesis with me, and he joined my group as a direct PhD student, and now he's in the last few months of his study, and we are expecting that he will defend by February 2023. We also collaborated with Dr. Ning Cheng from Canadian Light Source in Saskatoon, and Professor Wazni in Scarborough, University of Toronto, Scarborough, for DFT calculations. As I showed you before, we proposed this mechanism in one of our projects. And for example, for neodymium, we consider neodymium that is chelating with 3-nitrate and 3-TBP. And iron has the same structure for iron 3, and iron 2 was iron 2 with 2-nitrate and 2-DPP. We wanted to prove that this hypothetical structure is true. We performed DFT calculations with Professor Wazni, and we also performed X-ray absorption spectroscopy characterization in the Canadian Light Source in Saskatoon. These are the DFT models for iron and neodymium complexes. For iron 2, DFT predicted iron nitrate 2-TBP2, which is similar to what we proposed. For iron 3, it was iron nitrate 3-TBP3, again similar to what we proposed. For neodymium, 3 structures could be possible: neodymium nitrate 2-TBP4, neodymium nitrate 3-TBP4, and neodymium nitrate 3-TBP3. So we made these complexes after supercritical fluid extraction, and we took them to the Canadian Light Source in Saskatoon to characterize them with X-ray absorption spectroscopy. We looked at the structural coordination and interatomic interactions in the neodymium 3-TBP-HNO3 and iron 2 and iron 3-TBP-HNO3. And we performed density functional TOLE calculations to assess all potential mechanisms that I showed in the previous slide. And we validated these results by extended X-ray absorption fine structure, which is called EXAFS, and X-ray absorption near edge structure, XANES. This is the first time that these structures are characterized using this advanced technique. The results indicated or proved that iron 2 forms iron nitrate 2-TBP2, iron 3 forms iron nitrate 3-TBP3, and neodymium forms neodymium nitrate 3-TBP3, as we exactly predicted in our preliminary mechanistic characterization. In conclusion for the talk, management of Electronic waste can help conserve natural resources and protect ecosystems. It can also facilitate efficient utilization of materials and promote the circular economy. SCFE is an environmentally sustainable process for the recovery of rare earth elements from secondary resources. We successfully developed and optimized SCFE processes to extract rare earths from magnets and fluorescent lamps. We elucidated the extraction mechanism, and our most current work focused on XEAFS and XANES to investigate the structure of the complex molecules and provide metrical information about interatomic interactions between these cations and ligands. So we went from the macroscopic scale to microscopic scale in this process development. These are the highly qualified personnel contributing to this project. Bill Yao, my first master's student who initiated this work with me. After he graduated from master's, he went to Imperial Oil for 3 years, and now he's a PhD student at Calgary University. We have Jikai, my PhD student who will defend very soon, Dr. John Anavati, my former PhD student, Mr. Adrian Lambert, my former MNG student. I had 3 undergraduate students that are all graduated or they are in the end year of PhD, Nina, Erin, and Kimberly, and Miss Si-Cheng Lee, my current PhD student, who is also working on supercritical fluid extraction. I collaborated with Professor Yusuke Shimoyama in Tokyo Institute of Technology, and I hosted his PhD student, Dr. Nataina Kanust, during 2019. Professor Vasni is my collaborator for DFT calculations, and Dr. Nin Cheng, a scientist at the Canadian Light Source. At the end, I would like to thank all my sponsors over the past 8 years and all my group members, and thank you very much for your attention.